Welcome back to another episode of Continuous Improvement. I'm your host, Victor, and today we are diving into the world of Kubernetes. In this episode, we'll explore the key concepts you need to understand to navigate this powerful open source system for automating the deployment, scaling, and management of containerized applications. So grab a cup of coffee, sit back, and let's get started. Let's start with the control plane. This component plays a crucial role in making global decisions about the cluster. It consists of three fundamental elements: etcd, API server, and scheduler. Etcd acts as a distributed key value store, providing a reliable way to store data accessible by a distributed system or a cluster of machines. It ensures strong consistency while handling data storage. The API server serves as the interface through which users interact with the cluster. Whether it's through REST, a user interface, or the command line tool kubectl, the API server facilitates seamless communication and management. The scheduler handles resource management, ensuring that Kubernetes efficiently assigns pods to worker nodes while adhering to resource restrictions and constraints. Moving on to the data plane, this is where the resources, networking, and storage management come into play to enable container workloads to run smoothly. In Kubernetes, a namespace provides a logical separation of objects within the cluster. It scopes access and divides the cluster, allowing for better organization and management. Nodes, whether they are virtual or physical machines, form the backbone compute resources of a cluster. They are managed by the control plane and host pod objects. Kubelet is a critical component that acts as a control plane agent on each node, while the container runtime schedules and manages the pod containers. Kube proxy acts as a networking proxy within the cluster, ensuring smooth communication between pods. Now, let's talk about pods. These are the basic deployable objects in Kubernetes and can be seen as services or microservices. Pods can run one or more containers, sharing storage and network resources. Within a pod, you may have an init container to perform setup tasks before the main container starts, the main container hosting the application process, and even a sidecar container loosely coupled to the main container. It's important to note that pods are typically created via controller resources like deployments, daemon sets, jobs, or stateful sets. A replica set, for example, ensures a stable set of replica pods running at any given time. Config maps come in handy when storing non-confidential key value configurations. These can be used by pods as file mounts or environment variables accessible by the containers within a pod. Now let's explore the role-based access control, RBAC, resources. A service account provides an identity for all processes running within a pod. Cluster role and role contain sets of permissions, while cluster role binding and role binding grant those permissions to a specific service account. Deployments act as controllers for pods and associated objects like replica sets and config maps. They continuously monitor and reconcile the status declared in the manifest, making rollouts to replica sets seamless. Canary deployments, with garbage collection features, can also be executed. The horizontal pod autoscaler automates the scaling of workload resources based on metrics like memory and CPU usage. It can also utilize custom or external metrics for scaling, such as those provided by Prometheus. Storage class describes an abstract class of storage with properties like storage type, provider, and reclamation policies. It is utilized by persistent volume, which represents storage that can be attached to pods and has a life cycle independent of the pods themselves. Moving on to services, they serve as abstractions for network exposure. They provide load balancing and make pods accessible from other pods within the cluster. For stateful applications, there's the stateful set controller. Unlike deployment resources, it maintains a sticky identity for each pod and associates each pod with a unique instance of persistent storage. Deleting or scaling down a stateful set does not delete associated volumes. A job is ideal for applications that run tasks ending in successful completion. It deploys one or more pods and retries until a specified number of pods have terminated, signaling the task's conclusion. And for scheduled tasks, we have cron jobs, which operate on a set schedule. To guide external traffic to pods via services, we have ingress. Ingress requires an ingress controller, such as ingress nginx, to fulfill ingress rules. It can handle external load balancing, SSL termination, and name-based virtual hosting within the cluster. If you're looking to extend Kubernetes resource types, custom resource definition allows you to define custom resource properties and schemas. These can be subscribed to by custom controllers or operators, and each custom resource must have an associated custom resource definition. And there you have it, a whirlwind tour of important Kubernetes concepts. Whether you're preparing for the KID, CKA, or CKS exams or simply looking to enhance your Kubernetes knowledge, I hope this episode has given you valuable insights. Don't forget, if you have any questions or thoughts to share, feel free to reach out. Until next time, keep learning and embracing continuous improvement. Thank you for tuning into this episode of Continuous Improvement. If you enjoyed this content, don't forget to subscribe and leave us a review. And remember, your feedback helps us grow and improve. Stay curious and never stop learning. See you in the next episode.